previous session, we have seen the concept of directional derivatives, and we have seen a practical method to calculate the directional derivative using the gradient. And we have defined gradient and we know how to calculate the gradient. So let's recollect that first. duf at a point x naught y naught z. So this expression gives the meaning, or this expression denotes the directional derivative of the function f in the direction of the unit vector u at the point x naught y naught. Right. We have already told that everything we explain here in these sessions can also be generalized to any finite number of variables, or the functions of any finite number of variables. Now let's simply extend this to a case of three variable function. So obviously the notations say the same. Say x naught, y naught, z naught will be the notation, and let w equal to f of x, y, z be a function of three variables x, y, and z. Right. Then the directional derivative duf at say x, y, z is defined as we have seen for two variable cases. This can also be defined as a limit h tends to 0, f of x plus h cos alpha, y plus h cos beta, comma, z plus h cos gamma divided by h. So there are three more quantities involved here: alpha, beta, and gamma. They are nothing but the direction angles, or sometimes called direction cosines of the unit vector u. Right, which means alpha, beta, gamma are the angles made by the vector, the unit vector u, with the positive x-axis, the positive y-axis, and the positive z-axis respectively. So alpha is the angle made by u with the positive x-axis, beta is the angle made by u with the positive y-axis, and gamma is the angle made by u with the positive z-axis. Alright. So this is the formal definition of directional derivative of a three-variable function. But as in the case of a two-variable function, we will not be using this in general. Instead, we will use the formula with dot product. Right. Suppose we have a function w equal to f of x, y, z, and let u be a u be a unit vector. See, if you are thinking about a three-variable function, we'll be giving unit vectors in the space having three coordinates. Say some u0, u1, u2, maybe, or u1, u2, u3. That's the custom. u1, u2, u3. There may be three coordinates, and then the directional derivative of f in the direction of u at x, y, z can be found as gradient of f of x, y, z dot u, as you have seen before for two variable functions. So this just means that what we have explained for directional derivative of two variable functions can easily be excited or generalized for three variable, and this can easily be generalized to 4 or 5 or any finite number of variables. Right. So that's about case of three variables, and let's see an example that will make things a little more clear. Examples always help us to conceive things in a better sense. So find the directional derivative of f of x, y, z. Here we have a function capital F of x, y, z equal to xy squared minus 4x squared y plus z squared in the direction of the unit vector, or in the direction of the vector. We are not specifying it as a unit vector here. There's a reason. The vector, say r equal to 6i plus 2j plus 3k at 1, minus 1, 2. Alright. So we will use the dot product formula to find the directional derivative here. So the directional derivative du f x y z can be found as grad f dot u. So what is gradient of f here? What was gradient of f? How did we define gradient of x? Dou f by dou x I. We have capital F, right? Dou f by dou x I plus dou f by dou y j plus dou f by dou z k. So now let's partially differentiate these things. Let me clear this off since we have a shortage of space. So what is dou f by dou x? Dou f by dou x is, I'll write it as it is. So grad f equal to dou f by dou x I. So what is dou f by dou x? We keep y and z as constants and differentiate with respect to x. So first term will give y square minus 4 into 2x into y, so it will be 8xy plus 0. Right. Similarly, into I plus what is dou f by dou y? Similarly, we will keep x and z as constants and differentiate with respect to y. Will give 2xy minus 4x j plus differentiate with respect to z to obtain dou f by dou x will be 0 minus 0 plus 2z into k. Right. Now we are asked to find the directional derivative at 1, minus 1, 2. So simply plug in these values to this function. So gradient of f at 1, minus 1, 2 is equal to minus 1 square is 1 minus 8 into 1 into minus 1. This will be 8 into minus 1 minus 8, and this minus will be transferred to or changed to plus with this minus, with the minus from minus 1, right? So into plus 2 into x into y minus 1, so it will be minus 2 minus 4 into 1 4 j plus 2 into 2 4k. Right, let's try to simplify this. So can I remove this off? Yeah, okay. So grad of at 1 minus 1 2 equal to 9i plus minus 2 minus 4 is minus 6. So minus 6j plus 4k. Right. Now we have the vector r equal to 6i plus 2j plus 3k. We could use the formula grad f dot u if u is a unit vector. Is this r a unit vector? Let's see. What is mod r? Let's clear this off, right? We have that information here. So what is mod r or norm r? Square root of 6 square plus 2 square plus 3 square is equal to square root of, we'll consider only the positive roots here, 36 plus 4 plus 9 is equal to root of 49, which is 7, right? 49, root 49 is 7. We consider only the positive root here. So the absolute value is 7, not 1. So this is not a unit vector. So how can we make a vector r as a unit vector, or how can we calculate the unit vector in the direction of r, which is nothing but r by absolute value of r. We got the absolute value as 7 here. We know what is r. So the unit vector in the direction of r, u, can be found as r by norm r, which is r by 7. Okay, so r is here, so r by 7 is nothing but, or u equal to 6 by 7i plus 2 by 7j plus 3 by 7k. Right, so this is the u. Now we can calculate the directional derivative du f at 1 minus 1 2 as grad f dot u, which is nothing but grad f is here, u is here. So 9i minus 6j plus 4k dot 6 by 7i plus 2 by 7j plus 3 by 7k. You know how to calculate the dot product. Simply multiply corresponding terms and add. So 9 into 6 by 7 is 9 into 6 is 54 by 7 plus minus 6 into 2 will be minus 12 by 7 plus 4 into 3 12 by 7. Right. So this is 54 by 7 minus 12 by 7 and 12 by 7. So did I do some numerical mistakes? I don't know. So whatever, this is how we calculate the directional derivative of a function of 3 variables. Right. So the directional derivative required here is 54 by 7. Okay. So now let's think about the possible values of directional derivative. The maximum and minimum values of directional derivative. So let's think about the maximum value. Maximum value of directional derivative. Okay. So now let f be a function, whatever. Let it be a 2 variable, 3 variable or 4 variable, whatever. Let f be a function. And we know that the directional derivative at x, y, z. See, I don't write this x, y, z again. You may remember that these are functions of x, y, and z, or any number of variables. Duf is can be calculated as grad f dot u. Right. The directional derivative of f in the direction of u at any point can be calculated as grad f dot u. Okay. Then you know how to calculate the dot product. We have an equation connecting dot product as a dot b. If a and b are vectors having a magnitude and a direction, then the dot product a dot b is a scalar which can also be calculated as absolute value of a into absolute value of b into cos theta, where theta is the angle between a and b. Right, we know this. A dot b is ab cos theta. Okay, so if this is the case, duf can also be rewritten as, let's start from an end. So duf is equal to grad f dot u, which can also be rewritten as absolute value of grad f into modulus of u, or absolute value of u into, say, cos theta, where theta is the angle between grad f and u. You know that grad f is a vector and u is again a vector, it's a unit vector. Then we can think about the angle between these two vectors, and for that, using that angle, grad f dot u can be rewritten as absolute value of grad f into absolute value of u. These are real numbers and this is the usual multiplication of real numbers. Again, theta is the angle between grad f and u. Cos theta is again a real number. This is again a usual multiplication of real numbers. Okay. Now, what is this? This absolute value of u. U is considered, or u is taken as a unit vector. The absolute value of a unit vector is 1. Actually, for that reason it is called a unit vector. So this is 1. So multiplying with 1 doesn't make any change. So we can take that off. Into cos theta. Right. While we take this absolute value of u off, since absolute value of u is 1, since u is a unit vector. Here comes the analysis part. Now we have absolute value of grad f into cos theta. Right. What are the possible values of cos theta? See, how does the graph of cos theta looks like? Let this be 0 and cos 0 is 1. So this will be going like this. So however it go to either directions, the maximum value of theta, cos theta is 1 and the minimum value of cos theta is minus 1. Right. So the cos theta fluctuates in between minus 1 and plus 1. The values of cos theta fluctuates in between minus 1 and plus 1. So the maximum value of cos theta is 1 and the minimum value of cos theta is minus 1. using that fact, we can claim that the maximum value of directional derivative, see, if we have a fixed f, gradient of f is constant. We can think about changes in the unit vector, so theta may change. For that reason, the maximum value of directional derivative of f occurs when cos theta has its maximum value, that is 1. So the maximum value of directional derivative of f is the absolute value of gradient. The absolute value of gradient, since that's the point where cos theta assumes its maximum value 1, and the minimum value of directional derivative of f is f occurs at the point where cos theta takes its minimum value minus 1, so it will be minus of absolute value of f. Right. So in fact, the maximum value of directional derivative is nothing but the absolute value of gradient of f, and the minimum value of directional derivative is the negative of gradient of f. This just means that if you fix a function f and calculate all the possible directional derivatives in all the directions, the maximum value you will get will be absolute value of grad f, and the minimum value you will obtain will be the negative of absolute value of grad f. Okay, this is a very, very important concept in calculus. This can be used in very, very relevant practical situations. With a slight rearrangement, we can rewrite this as, see, we have seen that the maximum value occurs when cos theta takes the value 1. Cos theta is 1 means theta equal to 0. Similarly, minimum occurs when cos theta equal to minus 1, when cos theta takes the value minus 1. Right. So this is the point where this is theta equal to 0, 1, and this is pi by 2, and this is pi. Right. So if we have our unit vector in this direction, let's consider this to be 0, or suppose we have the function f in a specific direction. So let this be our direction of grad f. Grad f is a vector, so let this be the direction of grad f. So if u is in the same direction, then theta equal to 0. That's what we mean by theta, the angle between grad f and u. So angle is theta means they are in the same direction, and in that case cos theta is equal to 1, the maximum value occurs, and theta equal to pi means to make a angle of pi with this direction, the u has to be in the bank opposite direction. Right. U has to be in the bank opposite direction. This angle is 180 degree or pi radians. Alright, angle is measured in this direction. Okay. In that case where u and grad f are in the opposite direction, theta is pi and cos theta equal to minus 1, and in that case the minimum value occurs. Okay, the minimum value occurs in the case where u and grad f are in the opposite direction, and collecting all this information together, we can make a statement that this is a very important statement. The maximum value of directional derivative occurs when grad f and u are in the same direction. And the minimum value of directional derivative occurs when grad f and u are in opposite directions. Right. You know why do we say this? You have seen the analysis part. So the maximum value of directional derivatives occurs when the unit vector u is in the same direction of grad f. See, there is a certain point here. What do we mean by directional derivative in the direction of u? It's a derivative, so it actually is the rate of change of increase or decrease in the direction of u. Right? If it is positive, if the derivative is positive, we may say that the function is increasing, and if the derivative is negative, we may say that the function is decreasing. So whatever derivative actually measures the rate of change of the function, either increasing or decreasing. If it is a case, maximum directional derivative occurs in the direction of grad f means the direction of grad f is the direction of maximum increase. In other words, every function increases in a maximum rate in the direction of grad f. A function increases in its maximum rate in the direction of gradient. Similarly, every function decreases at its maximum rate in the opposite direction of grad f. The opposite direction of grad f can also be denoted as the direction of negative grad f. So every function, see, the minimum value means its maximum possible decrease, right? Since we have a negative possibility here, so every function decreases in the maximum rate or increases in the minimum rate. Both are the same. Increases in the maximum rate and decreases in the maximum rate and increases in the minimum rate. Both are the same. And in the opposite direction of gradient of f, or in the direction of negative grad f. Right. Things will be a little more clear if we consider an example. Right. So consider an example that the temperature inside a rectangular box is given by T of xyz equal to xyz into 1 minus x into 2 minus y into 3 minus z. Here x is in between 0 and 1 and y is in between 0 and 2, z is in between 0 and 3. Right. So we have a rectangular box, and the temperature inside that box is given using the function T of xyz equal to xyz into 1 minus x into 2 minus y into 3 minus z. This is not 2, this is z. Okay. Suppose we have an ant sitting inside this box. So as the temperature increases and cannot stay longer, so it may feel hot, so it may start moving. What you are supposed to find is to calculate the direction in which the ant has to move to escape from the heat as early as possible or as easy as possible. Or in technical words, or in the words of mathematics, you are actually supposed to find the direction of maximum decrease. The direction of maximum decrease. See, that is the safest direction. The direction of maximum decrease or the direction of minimum increase is the safest direction to move. Right? Or else the ant may get burnt. Alright. So you know how to find the direction of maximum decrease and minimum increase. Maximum decrease direction is actually given as negative direction of or the negative grad f. Negative grad f. So we have t here. So now we can simply find grad t. Grad t can be found as dot t by dou x I plus dot t by dou y j plus dot t by dou z k. Right. This is quite simple. We can find this. And when calculating the directional derivative, before moving any more further, suppose the ant is sitting at a point 1 minus 1, 1 by 2, or we have 1 by 2, 1, 1, let me check. Yeah, 1 by 2, 1, 1, is the point at which the ant sits. Okay, so the ant moves, start moving from this point. So you are actually supposed to find the gradient at this point. Alright, so when you try to differentiate this partially, you will have to use the partial derivative, since we have a term involving all x, y and z here, and we have terms involving x, y and z again. So you may have to use the product rule of differentiation, and whatever you use, the answer will be like, let me clear this off. The gradient will be like, I'll give you the answer and you have to work this out. Gradient xyz is yz into 2 minus y into 3 minus z into 1 minus 2x plus xz into 1 minus x into 3 minus z into 2 minus 2y j plus xy into 1 minus x into 2 minus y into 3 minus 2zk. So I suppose this is the answer. This could be the answer. And if you substitute 1 by 2, 1 and 1, you may get that gradient of t equal to 1 by 2, 1, 1 as 1 by 4k. All of these will be turned out, since if you substitute x equal to 1 by 2 in this equation, we will be having 2 into 1 by 2 equal to 1, so 1 minus 1 will be 0, so throughout will be 0. And if z equal to 1 in this equation, no. If y equal to 1 in this equation, 2 minus 2 into 1 will be 2 minus 2 will be 0, so throughout will be 0, so what will be left is from this part. And if you substitute and simplify, you will get 1 by 4k. Okay, so this is the direction of maximum increase. We are supposed to find the direction of minimum increase or maximum decrease, so which is nothing but the negative of delta t, which is minus 1 by 4k. So the temperature inside the box decreases in the maximum rate in the direction of negative gradient of t, which is minus 1 by 4k, where k is the unit vector in the direction of z axis. Okay, so this is the safest direction for the ant to move. Right. So similar questions are available in the textbooks and other worksheet available online. So you can simply find problems from there and try to solve them down. Alright, so this is how we make use of gradient to find to make applications in the physical problems.